Okay, so let's proceed with the study of n equals to gauge theories and 4 dimensions. So one of the goals which we set last time was to compute the low energy effective action, which today I will write in the superspace form. So I hope that Michael covered some of the superspace material. So that action which I wrote yesterday in components, which included the terms like the gauge coupling, which were dependent on the vacuum expectation values of the scalars. So this action can be neatly packaged into an integral over actually half of the n equals to superspace of the prepotential, where instead of the scalar in the vector multiplet, you substitute the whole vector multiplet. So some expression which I write symbolically as in this form. So it's a function on a superspace whose lowest component, which does not involve the fermionic variables, is a scalar in the vector multiplet. And then at 2 orders in the Grassmann variables expansion, you'll find the field strength. It will be the antiself dual part. And there are some sophisticated chirality conditions, which will actually introduce also the theta bar dependence. So n equals 2 superalgebra having 8 supercharges corresponds to the superspace having 8 8 odd directions, and you could choose 2 sort of holomorphic halves of these fermionic directions, and those would correspond to the n equals to chirals and then n equals to anti-chiral components of the action. And so we want to determine this part here. So to do that, we will employ a certain trick. So the trick, which actually happens to be quite useful on its own right. So the trick is now called the Omega Deformation. And the omega here stands for the rotation matrices. So the trick is the following. Suppose it works in any quantum field theory with global symmetry, let's say G, which, so let's suppose the theory lives in D dimensions, which can be lifted to D plus 1 space-time dimensions while preserving D plus 2, sorry. D plus 2. I'm writing. Most of what I write is correct. Most of what I say is not correct. So the idea is that if your quantum field theory allows the lift to D plus 2 dimensions with a global symmetry G, and then what you can do, you can compactify so let's call this quantum field theory prime, Strich in German, and so compactify quantum field theory prime on T2. So if you just compactify and send the area to 0, you get back the original theory. So nothing changes. But now let me accompany the compactification of 2 dimensions on a torus with the twist, with the boundary conditions so I pick two commuting elements in my global symmetry group G here. So I assume that they commute. And now I impose the boundary conditions that as I go, so this is my 2 torus. So if as I wind around the A cycle or B cycle, my fields are twisted by this global symmetry element G. Now let me take the limit when the area, which I will write as R squared, goes to 0, and GA and GB, they ascend to 1, but in such a way that so the velocity at which they approach 1 is proportional to the size of the torus. So then the claim is that as a result, we get a deformation of the original quantum field theory, and so the Lagrangian will be corrected by the terms which are proportional to omega A and omega B. Couplings, and well, the resulting theory might be easier to analyze than the original theory. Now, yes. So suppose you do it for the, suppose you start with ON model, for example. So for the single scalar, there is not much symmetry. There is no continuous symmetry. So you need at least 2. So my claim would be that, so if I call, so the global symmetry would be ON. So I think that the, so let me start with O2n for simplicity. Then, so I need to pick 2 commuting elements in the Lie algebra of ON. And so we can block diagonalize so we'll do the n blocks like that. So MA and omega B. So on. So we have n complex parameters in this omega deformation. Well, mu is probably not the best. So now, what shall we get? So my condition is that in d plus 2 dimensions, my scalars are twisted by the element of the rotation group. So you can expect that so giving a non-trivial expectation value to phi will violate my rotational symmetry, it would suggest that these boundary conditions favor the configuration where the scalar field is 0. That is to say that the scalar field will become massive. So so if I write my okay, so if I combine so I have two n scalars, I will combine them into n complex scalars. So this original action would be rewritten as z dz alpha dz alpha bar, and then so then these parameters would simply give me the masses for the scalars. So the omega deformed free scalar theory is just the massive scalar.
I'm sorry.
Yes.
One thing I forgot.
Okay.
It's important. Sunday we're going to start at 11 and not at 10 o'clock. There's an update program on the table, on the registration table. But the beginning is 11 and not 10 o'clock on Sunday. Okay?
What have we done? We changed from OM model to O2M model.
Well, I just multiplied n by 2, so that's what I did. I mean, if you take the ON model with n which is odd, then there will be always one scalar which will remain massless. You cannot. So the commuting.
Omega AB matrix.
Yeah. So the difference will be that there will be one block where it's 0. So it will be. So this is for the. So for 2n plus 1, this is the form to which you bring the antisymmetric matrix by rotation.
First we had omega A, omega B matrix from the group, and omega
from the real algebra, yes. So for the I'm just saying that for the orthogonal group with even number of acting in the space of even dimension, you block diagonalize it with 2 by 2 blocks, which could be in general all non-trivial. And if you have an orthogonal group in odd number of dimensions, then there will be one block which is 1 by 1, which is 0. That's it. Just saying that the rotation in odd number of dimensions always preserves one direction. So you can make massive all fields but one.
So this term is actually just comes from the kinetic term.
So, right. So what this term is actually, it's the gauge field. Actually, it's the VF of a gauge field of this O2n gauge field on the two torus. So what I'm doing actually, I leave my theory to two higher dimensions, and I turn on the gauge field in this global symmetry group. But I do it along the internal space, so I don't see it in the original space-time. Now, the interesting story is actually when this global symmetry group involves the Lorentz group. Yes?
I'm not sure. For me, it's not clear how you got the second term. So can you
Well, it's homework. Okay. So this it's very easy, actually. If I didn't make a mistake, but I think I didn't make a mistake. It's actually the same. I mean, it's a similar homework to the discussion of how you get the theory with massive adjoint hypermultiplet in compactifying d-phi brane on the two torus with the twist of the normal bundle. It's the same construction. So, I did not describe here the most general thing because my G, I only took G to be the global symmetry group in the sense that it did not touch the space-time symmetries. But what's interesting and what's with the trick which is actually, which I'm going to employ is to make G contain the space-time rotations. So this is the interesting part. And now we do the gauge theory on R4, on Euclidean R4. And so my G will contain a group of rotations. So these are the rotations of space-time. And so these matrices omega A and omega B will be essentially the, well, now they can be block diagonalized. And so you'll get two parameters, which are called epsilon 1 and epsilon 2. So the deformation of the theory which involving the rotations of spacetime produce a two-parametric deformation of the Lagrangian. So epsilon 1 and epsilon 2 are complex numbers, and they have dimension of mass. Because remember, the group elements by which you twist are dimensionless, but I take them to scale as the radius of the torus, which I send to 0. So this is dimension of length, therefore this has dimension of mass. And so whatever theory we start with, we get some kind of massive deformation in the theory. But now it's a tricky massive deformation because since I'm now using the rotations of spacetime, I'm breaking the translational invariance. So the Omega deformation breaks translational invariance. And you can actually guess already from the example with the scalar field where what deformation did, it sort of localized in the field space near the region where the field was equal to 0. Now that I'm involving the space-time rotations, I will sort of localize my physics in space-time. And so effectively, what this deformation does, it makes the interesting physics to live in the box of the size of the order 1 over epsilon in space-time. So this is. Say again? Well, I use the rotation, so I had to choose a point about which I rotate. So that was the primary choice. And then, so it is a kind of an infrared regulator, but it is not a conventional infrared regulator where you just put a sharp box. It's something trickier. If you work it out, so if you work out Lagrangian for the gauge theory, for example, well, you will get that the standard Lagrangian for n equals 2 gauge theory, so this is a standard Lagrangian, gets deformed to, let me put here a coupling constant. Plus well, there are some other terms, where V is the vector field which generates the rotations. So there is explicit space-time dependence here. And if you just collect, for example, all the terms which involve the field strength, what you will see is that effectively so effectively what you are doing, you get the space-dependent coupling constant, gauge coupling constant, which starts to be finite at the origin of rotation and then becomes extremely weak far away. So here we get extremely weak coupling. And here you get the old physics. So nothing changes compared to the original theory. So why is it important? Well, we are ultimately after trying to integrate the over the modular space of instantons. So we want to take into account the instanton effects in some efficient manner. And so if you look at the instanton action, which normally is just e to the, well, goes like e to the minus 8 pi squared over g squared and some normalizations. So here, this is the instanton action which is independent of where this instanton is in the ordinary situation. Now it will start depending on the position of the center of mass, of the center of the instanton. So the instanton measure will get corrected by this amount. And so what it means is that it forces your instantons to sit within this box. So omega is of the order of epsilon. And so this is Gaussian factor which makes them sit in the box of the size 1 over epsilon. And so that's how you...
There's no dependence on the scale?
There is a dependence on the scale. Everything, of course, this is just the simplest factor of...
But it also cuts off.
Right. So the instantons, but the fact that the instantons don't want to be too large is already taken care of by the Higgs field, actually. So that's... okay. Yes?
I mean, this trick did not rely at all on being n equal to 2.
Well, I mean, the trick can be done in any theory with the symmetry, but whether the theory which you get will be under any control and continuously connected to the original theory, it's a separate issue. So here, of course, the important part of the story is to make such a deformation which will preserve some kind of supersymmetry, so that what I will compute will be exact. So I didn't get there yet.
In principle, you could have reversed this equivalence and claimed that you can discuss theory D plus 2 in terms of theory, massless theory in D?
Well, I'm not sure. Well, sometimes you can.
With zero-size torus.
Yeah, but if zero-size torus is the same as this d-dimensional theory. What you can do sometimes, if you have supersymmetry, you can actually you don't have to scale the torus to zero size. So you can actually discuss some effects of the finite size torus. But without supersymmetry, I don't think you could do that. Anyway, so now indeed, so as Kobe mentioned, we should say something about the supersymmetry. And so if we are in n equals 2 situation, then the global symmetry group involves also the so-called R-symmetry group. So this is the SU2, which rotates n equals 1 SUSY is into each other. So the supercharges, we have two kinds of supercharges. And so these are, so if I write my global symmetry as SU2 cross SU2 left, well, 1 cross SU2 plus minus, So there are 3 SU2s in question. And so this guy transforms as, let's say, spin 1/2 under the R symmetry group, spin 1/2 under the plus, and spin 0 under the minus. And this guy transforms as spin 1/2 under R symmetry, spin 0, spin 1/2. Now, if I just do the rotation, so if I use the general rotation as I did here, my epsilons have to do with this part of this global symmetry group. So more precisely, epsilon 1 plus epsilon 2 corresponds to the plus part, and epsilon 1 minus epsilon 2 corresponds to the minus part. So if I look at my spinors, which generate supersymmetry, and transport them around that about this phantom 2 torus, they will transform non-trivially. And so I will break supersymmetry if I only did that. Fortunately, I also have this transformation. So I can compensate by, so for example, if in addition to the rotations, I will also turn on the Wilson line in that R symmetry group. For example, I could make it transform with the minus epsilon 1 plus epsilon 2 parameter. Then what will happen is that these guys will survive, and these guys will disappear. Because if epsilons are non-zero, and if epsilons are generic, then this picks up a non-trivial phase under the holonomy, and so does not lead to the conserved charge. But these guys will lead to the conserved supercharges. And so we get some kind of fermionic symmetry of the resulting theory. Yet it's an interesting symmetry which cannot be a usual supersymmetry, because usual supersymmetry commutes to translations, and translations were broken. So what happens is that these guys will produce a rotation. So we'll get the supersymmetry algebra. So out of these Qs, there is one Q which you can construct, and its anticommutator with itself will be a rotation plus gauge transformations. So it's a modification of the Poincare algebra. These days it's not so unusual because you find such things in anti-de Sitter algebras all over the map, but when this was found, it was sort of surprising. Anyway, yes?
So, translations come from QQ bar.
Right.
Q bar did not
Disappear.
survive,
so there is no surprise. It's consistent, yes, it's consistent. But the fact that you pick up a rotation which wasn't there, you have to work it. You have to work a little bit. You see, the theory is deformed, and superalgebra is also deformed. But it's there. So the claim is that there is a way to supplement this Lagrangian with fermionic terms such that it will be invariant under some fermionic symmetry. And that's important because that allows, for the computations which we are going to use, you can modify the action by adding Q-exact terms in such a way to localize the path integral. And what will it localize to? It will localize to the integral over instanton configurations. Just one second. So the original path integral will become now a sum of instanton charges, and then the integrals over the instanton moduli spaces of some measure, which I will now describe what this measure is. Yes?
What happens if you have central extensions in this QQ?
Well, it's also there. So plus whatever. In fact, this rotation is also kind of a central extension term. Because it corresponds to the charges, so the angular momentum. which is then. Okay, so you need to look at this action and evaluate it on the instanton background to understand what is the measure. So let me just present the result. The result is the following. So first of all, what is this module space of instantons? So this is the space of solutions to the equation f plus equals to 0. Let's say on S4. So we work on R4, but it's convenient to add a point at infinity so they have the finite action. So they extend to S4, and they approach trivial gauge field at infinity, trivial up to the gauge transformation. And we divide by the gauge transformations which approach 1 at infinity. So that this space, it has dimension which is 4 times the instanton charge times the number of colors for the SUN gauge group, or for UN gauge group. And so the instanton charge is equal to n, little n. Now, on this space, the group of constant so the ones which we did not divide by, they still act. So they form the group UN. So this is the group, our gauge group. And also the rotations of R4, which is S4 minus infinity, they also act. There are also translations which act, but I will not care about the translations. And so let me call the parameter of the infinitesimal gauge transformation A, which is the same A as the vacuum expectation value of the Higgs field. So that generates the constant gauge transformations, and the parameters of the infinitesimal rotations are our friends epsilon 1 and epsilon 2. So we have a large group of symmetries which act on this which acts on this space. So let me denote by V of A and epsilon the vector field on this moduli space, which corresponds to the infinitesimal gauge transformation at infinity and infinitesimal rotation. So if you go back to the original field variables, this vector field, it's not vector field, it's not a gauge field, it's a vector field in the sense of infinitesimal transformation. So it corresponds to the change in the gauge field by the infinitesimal gauge transformation generated by phi, which is this guy. Now that the fact that it is constant means that this is just the commutator, plus the infinitesimal rotation. Now the rotations act by Lie derivatives, which you can actually rewrite in this case in this way. So what I'm saying is that I take an instanton gauge field configuration and vary it in this way, and then you'll get another instanton configuration, modular gauge transformations. And so this transformation expressed in terms of the moduli, so you can write this as the variation of the So you can write it as a variation of the moduli. And so this is the vector field which I'm talking about here. Yes.
Is epsilon still complex?
Yes. So this is actually a complex. It's a complex vector field. Just like because so just as A's are complex, because this phi is a complex Higgs field, so these omegas are also complex. And in order to keep them complex, this is why we need to live to d+2 dimensions in the original construction. If you live to d+1 dimensions, you can also do that, but then you get a real parameter. But what's important is that in this story with this supersymmetry, A and epsilon are Q closed, but A bar, so all the A bar dependence and epsilon bar dependence is in Q exact terms. And so you can play the trick of sending A bar to infinity and epsilon bar to infinity while keeping A and epsilon finite. And that's what localizes things. Okay, so the measure which you get here is the well, it has the bosonic and fermionic part. I will write the bosonic part. The bosonic part is just the norm squared in the metric, which is the metric on the instanton moduli space. Of the vector field so and that's actually this part comes essentially from this term in Lagrangian. So what you want to integrate over the instanton moduli space is the exponential of the minus norm squared of the vector field which generates this infinitesimal symmetry. And now the A bar dependence is here and also here. And it is such that as you change epsilon bar or A bar, this measure changes by a total derivative. And so if you know that your integral is convergent, and that's the tricky part, then you can actually simplify your life by doing what I just said here, send A bar and epsilon bar to infinity. So the measure then localizes onto the locus where V simply vanishes. And so instead of the integral over the modular space of instantons, this is some horrible space of which we don't know much. We know its dimension, we know something about it, but we don't know it in sufficient detail to perform these integrals explicitly. But if we are lucky, then this, see, I have as many equations as I have my moduli. So these are the moduli. And so hopefully this will just localize me at some number of points. So these are called the fixed points of the symmetry. Okay. Yes, of course. This is already on the modular space of instantons. So the gauge group was divided by. This is all written in the. Okay. I don't really want to get into discussion, but okay. So think of. You can think of it as. How should I say this? Okay. This derivative with respect to the moduli shouldn't be understood in gauge invariant fashion, actually. So, okay, since Kobe is asking, I'll spend a few minutes. So let me go back to this formula, actually. what I wrote here was some parameterization, some arbitrary parameterization of the instanton solution. So for every value of my moduli m, I have an instanton solution. Now, of course, different people have different gauges, so this description is not gauge invariant. Now, when I differentiate with respect to the moduli, this expression, what do we know? We know that for every value of m, the curvature of A is anti-self-dual. So this guy will definitely obey the linearized instanton equation. But now the space of solutions to linearized equations contains also linearized gauge transformations. So we want to project them out somehow. So, and one way which is natural from the metric point, from this metric point of view, is to impose the Lorentz gauge. Well, maybe it's Lorentz or Coulomb gauge, depends on the pace. Since we are in Euclidean space, so this is the gauge choice. Okay, so what you, sorry, no, I shouldn't say it this way. What I should say is that now when you, sorry. So when you differentiate, what you get some solution of the linearized self-duality equations. Plus, perhaps, a gauge transformation, infinitesimal gauge transformation, which depends on the direction in the modular space at which you are pointing. So these guys are these are the so-called zero modes, which are normalized. So first of all, they obey the linearized instanton equation, and then they obey the my gauge choice. So I'm choosing the background Coulomb gauge, Lorentz gauge, for every I. So there are these compensating gauge transformations which one performs in differentiating, and so what I should put here is a covariant derivative. So what I put here is really the norm of the scalar product of these linearized modes which obey the gauge choice. So what I wrote previously should be was to be understood in the following sense: that you take any variation of the instanton gauge field, and then you minimize with respect to the choice of the compensating gauge. That will actually enforce this gauge condition. So this metric is gauge invariant. The bottom line, the metric is gauge invariant, and this is gauge invariant. So this is a well-defined expression. Okay, so there are this. So now we need to talk about the fixed points. Well, the bad news is that okay, what are these fixed points? First of all, so these are the instantons which are invariant under their global gauge transformations, which means that these are the zero-size instantons, because whenever you have a non-zero size, there is a notion of the gauge orientation to infinity, and that's not invariant under gauge transformations. So they have to be of zero size. So these are points like instantons which can be anywhere, but now we also have this rotational symmetry. So now they have to be invariant under rotations, which means that all have to sit at the origin in this potential well which was created by the Omega deformation. So indeed, this is an isolated point. In fact, it's just one point. But it's a very horrible and complicated point, because that's the most singular place in the instanton moduli space where you could be. And this is actually beyond the gauge theory, because already the point like instantons, these are not the gauge field configurations. This is something which is it's an idealization of the gauge configuration. So I need one more trick to resolve the singularity. And this trick is called the non-commutative deformation. I mean, by now there are means of dealing with these singularities, but originally there weren't any. So say again?
What do you mean by that statement?
There are, well, mathematicians, well, also physicists have learned how to deal with singular spaces and integrals like those of an integral over singular spaces. So
Without limiting or deformation?
without non-commutative deformation. Yeah.
Some limiting process? Or, how do you
Well, you have to, I mean, you use the fact that this space, this modular space of instantons, sometimes is a quotient of something smooth by the action of the group. This group has nothing to do with the original gauge group. It's for example, for the UN instantons, it's the quotient by the U little n, the instant number. And so when you have to do this integral, you can sort of lift it to the smooth part, and then do the counter deformation. So you will still get some set of fixed points, not this very singular thing, but it doesn't. Unlike this non-commutative deformation, which is an understandable deformation of the gauge theory, this is just a mathematical trick for which I don't know the physical interpretation so far. Okay, so the trick. So we need one more trick, which will actually prevent our instantons from becoming really point-like. So the trick which will keep the instantons from shrinking. So if there is some mechanism which doesn't allow the instanton to become smaller than some size, then you get a problem which looks much nicer now. You have a potential well where you have a number of particles which cannot be too small, which try to be very close to each other, but since there is some minimal distance, you have some equilibrium configuration. And so you'll have several equilibrium configurations, and we'll just have to enumerate them and sum over all of them. And so this trick is a non-commutative deformation. I don't really have time to explain what it is in all detail, but I can tell you what it leads to in terms of the solutions of instanton equations. So it turns out that in 2 words, what you do, you replace the gauge theory where the Lagrangian is written using the ordinary usual products of functions on spacetime. You replace it by the so-called Moyal product. So you introduce one more dimension full parameter, the effective matrix, the antisymmetric 4x4 matrix. And it turns out that this deformation can be done in a way which is consistent with the supersymmetry Q, which is preserved by the Omega deformation. And in fact, all dependence on theta, on this non-commutativity parameter, is again of the Q-exact term, of the Q-exact form. So it will not affect our computation. But the point is that this has dimension of length squared. So that introduces a minimal length into the system. So what we did, so far, we introduced the maximal length in the system, which was 1 over epsilon. And we introduced the minimal length in the system, which is square root of theta. And epsilon was an observable parameter, and while theta is not observable, as far as the computations of the Q-closed observables are concerned. And now,
would it be the same if we put some small number to the right side of ADHM construction?
yes, this is what it amounts to. You're right. This is what it amounts to. Right. This is how it was invented. Now, what happens after this information is that the U1 theory starts having non-singular instanton solutions. So there, in the ordinary Maxwell theory doesn't have non-singular instanton solutions. It actually has interesting solutions which are which have a singularity at a point. And after this non-commutative information, they actually, sort of become smeared out. And actually, this is in accordance. some sort of zeta regularization. This is what you get from the ratio of determinants. And when epsilon 1 and epsilon 2 go to 0, this function gamma has the asymptotics whose leading term is precisely the perturbative prepotential, which I talked about yesterday. So it has a singularity when epsilons go to 0, and the leading coefficient in front of this most singular term is this x squared log x famous function. Okay, so the partition function of the gauge theory, so this full path integral of the gauge theory after the Omega deformation was implemented becomes, well, it's actually, so it's a product of a perturbative piece, which I didn't have time to talk about, which actually was included here. So, so it's a sum over n from 0 to infinity. We put here the instanton weight, which for convenience I will call lambda to the power 2 capital N small n. And then there's a sum over all n tuples of Young diagrams with the condition that the total size is equal to little n, and then you put this energy function, this energy function. So the problem of evaluating the path integral of gauge theory becomes a problem of computing the partition function of the ground canonical ensemble of these Young diagrams. And so far I present the result for the pure UN gauge theory. There are similar expressions for whatever gauge theory with fundamental or bifundamental or adjoint hypermultiplets you can imagine. In fact, for any representation of the UN gauge group, you can write down a similar formula. So the basic ingredients, namely the sum over the n-tuples of partitions, is universal. This is just the fixed points on the instant modular space. It's the energy of the configuration which changes from one theory to another. And then, if we are interested in the original gauge theory, which lived in flat space-time, well, we need to send epsilon 1 and epsilon 2 to 0 to remove the Omega deformation. Now, so we have this partition function z. And we think about this as of the thermodynamic quantity. So it's a ground canonical ensemble of instantons. And as we discussed, effectively the instantons live in a box of finite size, 1 over epsilon. Now, well, you would expect the partition function to behave in the extensive fashion, so it should go like the volume. So the limit when epsilon goes to 0 is like the limit when the volume goes to infinity. So when the volume of a system goes to infinity, the partition functions typically behave in extensive fashion. And the interesting quantity is the free energy, so the free energy per unit volume. And now, there is a little subtlety here, namely, epsilon was of dimension of mass, so the volume naively would be of the order of 1 over epsilon to the 4th power. But in fact, so this would be 1 over epsilon 1, epsilon 2, epsilon 1 bar, epsilon 2 bar. But as I argued earlier, the epsilon bar dependence has to cancel out because of the supersymmetry. So what happens is that you actually get not the volume, but the super volume. Remember that the original theory lived in the superspace. And it turns out that epsilon bars, every epsilon bar comes with 2 thetas. So remember, in supersymmetry transformations, the supercharge is it's a square root of a translation. The translation has dimension of mass, so the supercharge has dimension of square root of the mass. So thetas are worth square root of the length, and so this is a dimensionless quantity. So when you take into account the fermionic part, you'll actually recover epsilon bars in the numerator, and so they cancel out. So the super volume is 1 over epsilon 1, 1 over epsilon 2. So this is this is what stands here, and we had the prepotential as a measure in the effective action integration over the superspace, and so that would be the free energy. So this is the free energy. Now evaluated as a function of A. So the conclusion of that small discussion is that when epsilon go to 0, you will recover the prepotential of the gauge theory as the leading singularity of the partition function. Now, the subleading terms are also quite interesting for the gauge theory, but I will not discuss them. So this is the prepotential of effective theory. So now we have an explicit formula because we have an expression for the full partition function as a sum of the Young diagrams of something which is very explicit. And we need to evaluate the asymptotics of that partition function in the limit when epsilon 1 and epsilon 2 go to 0 and we need to extract the leading term. So not surprisingly, you see, in this Young diagrams, in this geometric picture of Young diagrams, the sizes of these boxes were proportional to epsilon. So when epsilon goes to 0, these little wiggles become smaller and smaller. And you can expect, and you can actually mathematically prove, that when epsilon goes to 0, while a's are kept fixed, there is one dominating configuration of Young diagrams with a very large size. So the instanton number would be of the order 1 over epsilon 1 over epsilon 2, for which these violet curves will actually be continuous. So you'll actually get something so it's a curve which starts as a linear function, but then smoothly, but not infinitely smoothly, will start changing, and then it will go back to being linear again. And then for the second, and for the third, and so on and so forth. So in the limit, what will happen is that this function f of x, this is called limit shape. It's something which probabilists studied a long time ago. You get it from, well, roughly speaking, the area of each box is epsilon 1 times epsilon 2. I claim that I get a smooth curve, which in the units where A1, A2, and AN are finite is finite, so it occupies some finite area. There is some finite area below it. You see, it doesn't go all the way to infinity. It actually starts as a linear, and then there is some finite area here. And so it's n times epsilon 1, epsilon 2 equals something finite. So therefore, and actually this is what you expect because I said that this is like the volume. So this is like the volume. So having the number of instantons proportional to the allowed volume means that you get some specific density of instantons, which is determined by the Higgs field, which is what you expect in the original theory. In the translation invariant theory, you expect to have some equilibrium density of instantons. And it's very small in the region where the Higgs field is very large, which is also what you expect. You expect to have a dilute instanton gas. And this is what you get. Okay. So so we need to find the expression for this function f, and that we get by minimizing the energy subject to all kinds of constraints. That so there are some gaps here, and this minimization. So there is some minimization problem. And you solve this minimization problem by the techniques which are sort of similar to the techniques you solve the matrix models in the large n limit. So let me say just one last thing about this. So introduce a function y of x, which is exponential of the integral of f double prime x prime logarithm of x minus x prime. And 1/2. So this is a function about which you know that it behaves as x to the n when x goes to infinity. And it has cuts in the complex plane somewhere around A1, A2, AN. So these are the points where this function f stops being precisely linear. So you see, when f is linear, f double prime is equal to 0. And so when f double prime is non-zero, so when it has a support, this is where this function has cuts. And the equation for the limit shape translates to the condition that y plus lambda to the 2n over y is a single valued function of x. And actually that makes it a polynomial of degree n. And this is precisely the Zabir-Putin curve. So this is how you solve this problem. And so this is how you derive the Zabir-Putin curves. And then you can check that you got the correct conditions for the periods. And so the prepotential will precisely be, so you identify A's with the periods of the differential x dy over y, and A duals, which are the derivatives of the prepotential with the other periods. So in this picture, A cycles go around the cuts. These are the A cycles, and the B cycles go between the cuts. And so if you take two copies of the x plane, so the x is like it's some kind of a complexification of the horizontal line here, and open up the cuts. there is actually singularity at infinity. Well, I'm not drawing 9 holes here because the Hanukkah is over. So, and so then you take the second copy, and you get the complete curve. And so these are the singular. So this is where the x goes to infinity, here and there. And so that's the Seiberg-Witten curve for 1, 2, 3, 4 for U4 gauge theory. And then you just. And I think it's a good place to stop. Okay.
Could you maybe clarify at this moment about localization that we can add to the action some Q-exact terms?
Yes.
But how exactly in this case do we add something? Some Q-exact terms or?
Well, so here I vary a parameter. So I vary a parameter which is a bar and epsilon bar, and the variation is changing the action by the Q-exact term. So all the terms which involve a bar and epsilon bar are Q-exact. So variation is also Q-exact. That's the.
And we send them to infinity.
Yes.
And that localizes our theory to.
And so that makes the measure sharply localized at these fixed points.
You argue that the partition function at the leading limit of epsilon to 0 is the exponential of the prepotential. But the prepotential is not the electromagnetic duality invariant.
Right.
So how do we reconcile this?
So this partition, but as I said yesterday, the electromagnetic duality is not a symmetry of the theory. It's some kind. It's a statement about how should I say this? You see, this partition function was defined in a particular, if you like, in a particular electromagnetic frame, where I viewed my theory as a gauge theory with a particular Lagrangian, which had a symmetry which I used in this Omega deformation. As you change the as you change the vacua, as you vary the parameters, you might go to the region in field space where it is more adequate to describe the theory in some other terms. And so then you'll get a different definition of the partition function, Z. And the claim is that there is a non-trivial transformation, so between the electric definition of the partition function and the magnetic definition of the partition function. So they're both defined, and they are related by a transformation which is similar to the electromagnetic transformation in the original theory, but it's a little bit trickier. So it involves some kind of Fourier transform.
You mentioned that this construction applies also for a product of gauge groups.
Yes, yes, of course, of course. Yes.
Do I understand correctly that you introduced this Omega deformation just to deal with zero modes of the shift symmetry?
Not only the shifts, but shifts in particular. Yes.
So, but to introduce, for example, just a box, we don't want to do that because it spoils supersymmetry.
Right.
Okay. What about zero fermionic zero modes? For instance,
It takes care of all so the fact that you get localization at fixed points means that you get rid of all zero modes, both bosonic and fermionic. You see, of course, there are ways of putting system in a box while preserving supersymmetry. You can, for example, place it on the torus, but then that leads to unwanted fermionic zero modes, which you cannot get rid of, and which just make the whole thing vanish, which is sort of not interesting.